In this video I will talk about the stability of the submerged and the floating objects. In the last video we did look at exactly why some objects will float and why some will sink because of the buoyancy force and everything, but in this one I will talk about the stability. And let's actually look at and stability of the submerged and the floating objects. So let's look at the conditions. So first let's look at the what is stability. stability. Alright, so what we mean by stability is, so let's look at a completely stable object. So if this is a completely stable object, so the case would be, you have a curve that goes like this and you have an object. So basically doesn't matter where you leave this ball, okay, so it will always come back to its stable position. So this is complete stable object. Doesn't really matter how much you change the position of this ball, it will always come to this position. So this is stable, and then you have something which is called neutrally stable. So the neutrally stable object is, condition is somewhere like, let's suppose if you have a flat plane and you have the same ball here, and then you give some disturbance to this ball. So basically you move it up till this point. So it's not gonna come back to its own position. What it will do, it will basically come to this new location, and that is its new stable position, because it's not going anywhere. Even if you provide small disturbance, it will go to a new stable position. So it's neutrally stable. Another case is when it's unstable, okay, which is the case, so it's basically the opposite of this curve. And okay, so now you have an object sitting over here, so any disturbance you would provide, it basically will fall from that cliff, and it's at a very unstable position. So any disturbance will actually roll it down, and it will completely change. It cannot come back to this position again. And then combining some of these, you can have actually a conditionally stable situation. And this is really important for the floating object. So the conditionally stable, and it looks something like, so if I have to draw something like this, you can think about it something like that. And then you have this object sitting over here. So if I give it a small disturbance, it will come back to its, so if I give some small disturbance, it will come to its stable position. But if our disturbance actually is bigger than a threshold, which in this case is this hump, so if I basically give a disturbance which actually goes beyond this hump, then it's not going to come back. So it is conditionally stable. It will be stable in this region, but anytime we can pass that threshold or that hump, it basically will roll down and it becomes unstable. So this is an important idea for the floating objects, especially for ships, because they can tilt at certain angle, but once they pass through a certain angle, they will up till a certain angle, they will basically come back to their stable position. But if the angle basically goes beyond this threshold, then they basically will capsize. So it's important concept in the floating objects, but we will get to that. But let's actually look at the submerged objects. And submerged objects, there are examples. A blimp can be a submerged object because it's completely surrounded by the air. The other one is actually a submarine, because it's completely most of the time is inside the liquid. So let's look at for submerged bodies, and then we will look at the floating bodies. So for submerged bodies, to be stable, so for submerged bodies to be stable, center of gravity which I am representing with G, okay, so G should be lower than the center of buoyancy, should be lower than center of buoyancy. Alright, so one of the if I have to draw this, so okay, so the center of gravity should be lower than, so somewhere over here, because we have the buoyancy will be acting at the centroid of the shape. So this is where the centroid is, so I can define this point to be B, and this force is F of B. And so the center of gravity, which can be some point over here, and that's where the weight is acting. So that's where the weight is acting, and I'm representing that with G. So now the idea is the center of buoyancy is the centroid, which is the center of geometry, and the center of gravity is where the whole weight is acting. And you can think about it like if you have a submarine which can have more weight here, so if you have more steel here, so mostly weight will be occupied in this area, and then if this area is air, so then that does not contribute to the total weight of that, and that's why the center of gravity can actually be below the center of geometry. So that's why the center of gravity is below the in this case. So if that is the case, then the submerged body will always be stable, and that's what you want to do for the cases in submarines. Okay, so that's what you want to do in the cases of submarine, and of course there are some stabilizer and everything, but if this is the case, they will always be, of course, yeah. And the other case is so the idea is if there is a small tilt, so what will happen is, so for the same object, if there is a small tilt, so you have this center of buoyancy acting somewhere over here, but now the center of so this is at the center, this is B, and then if you give it a small tilt, the weight will be somewhere over here. So now it will try to create a restoring couple, so this will create a restoring couple which will bring it back to its stable position. But in some scenarios you can have the opposite. So let's suppose, so this is the case for the submarine, but if you have the central buoyancy somewhere over here, and then this is represented with B, and then your weight actually acts somewhere over here where is the center of gravity. So now if there's a small disturbance, you still have the center of buoyancy here, but if the weight if you rotate this, the weight goes here to the point G, so now it will create like an unstable couple, or like, so this is completely unstable because it will try to overturn it so that the buoyancy goes on the top and weight actually goes at the bottom. Okay, so this is for the case for the submerged, which is pretty straightforward to understand why this happens. So for the case of the floating objects, so for the floating objects, the body will always be stable if G is lower than B. So again, what we discussed earlier, so the body will always be stable when G is below B. So the same idea applies. So if this is your fluid layer, and somewhere over here you have this floating object, so as long as the weight is acting below, so this is your G, and somewhere over here is your buoyancy force, and this is the point B. So as long as G is below B, okay, so when G is below B, it will always be stable. Okay, so however, a floating body may still be stable when G is directly above B. Okay, so for certain scenarios, and again we will talk about that if the G is above B, it will still be stable, and that is the case for the cases of the ships and all that, because you have a much higher mass on the top, and then they do displace the fluid, but not as much compared to the total size of this object. So the weight or the center of gravity will be somewhere above the center of buoyancy, but they still will be stable under some conditions. So let's look at the stable when they will be stable. So a small tilt ship would come back, but when the tilt is large, the ship actually will capsize. So for small tilts, ship will come back, but for large tilts, ship will capsize. Okay, so the important quantity which tells us when the ship actually will be stable, we have to actually get a new quantity which is called the Metacenter to measure the stability. We need to find Metacenter, and we will discuss how actually we can calculate that and what it actually tells us. So we need to know the Metacenter. Alright, so let's actually first look at how we can actually find the Metacenter. So I will so let me just draw the first let me give a definition of how we can find it, and then I will show you by drawing a picture. So okay, so a floating body is stable if its center of gravity is below the Metacenter. Okay, so a floating body is stable. Okay, so it's stable if its center of gravity, which I'm representing with G, is below Metacenter, which I am representing with M. Okay, so a floating body is stable if its center of gravity is below Metacenter. And again, how do we calculate that? The way we calculate this, a vertical line drawn upwards from B, okay, which is the center of buoyancy. So a vertical line drawn upwards from B intersects the line of symmetry, and that is important, by weight at point M, is called Metacenter. Okay, and so let's actually take a look at exactly how we'll define this. So a vertical line drawn upwards from B intersects the line of symmetry by weight at point M. So if I have to define the Metacenter, so let's just take the first case. We have a ship or like something which actually is at an angle. Alright, so if this is slightly tilted, alright, so okay, I just made it too big, but okay, so the idea is if this thing is tilted, so this is the fluid that's been displaced. So somewhere over here we will have the buoyancy force. So the buoyancy force is acting in this direction. So what it says is a vertical line drawn upwards from B. So it will give me this line over here. And the second thing is intersects the line of symmetry by weight. So where the weight of this object is acting, so somewhere over here, but then I have to, so the total weight of this object, it can be somewhere over here. So if the total is W, so half of W over 2, so where you split this into half, so that's the line that we are looking at. So I can this point is the G, where the center of the where the weight is acting, but then I have to divide this into half of the weight here, half of the weight here, and where these two lines intersect, this point I am calling as M. So as long as M is above G, this will be stable. But if I keep on, and then let me just give you an exaggerated view of the same thing. So in this case, yeah, so now the idea is, if we make it a huge tilt for this object, so something like this. Okay, so yeah, and this is just too much, but now the idea is, if you think about it, somewhere over here will be the buoyancy force, and somewhere over here is our weight. Alright, so if I go this way, I have this. No, actually it still is that. Yeah, I mean, so the idea with this is, in fact, I shouldn't be drawing like this. So alright, so let me actually not the easiest of the pictures to draw, but okay, so let's suppose if that's the case, so your buoyancy force is acting upwards in this direction, the weight is actually somewhere over here. So now where these two intersect, that's where your metacenter is, and it actually is below your center of gravity, and this is your point B. So now the metacenter is actually below the center of gravity, and if you think about it, so from this point it will try to create, so this is your point M, this is your point G where the weight is acting, so this will try to create a turning couple over here in this direction, so it will try to rotate it. But if you look over here, so even if you create a small disturbance, the weight is, so the weight will try to restore it back to its stable position. So that's why as long as M is above G, it will be stable, and once the M goes below G, it will become unstable. So at least that part is for the definition, but we will look at how we actually calculate this, how we actually find out this metacenter. Alright, so to calculate this metacenter, okay, so before I do that, so let me just give you, I will show you the procedure, but let me just define something else. So the distance to metacenter from the center of buoyancy is called MB. Okay, so and again, how do we calculate MB? MB is equals to I over VD, and let me just show you. So this is the point where we had the buoyancy, so this is the point B where the buoyancy was acting, and the distance from here to the metacenter is represented as MB. Okay, so that distance is MB, and we calculate this as equals to MB is equals to I over VD, and where VD is the displaced volume of the fluid, and I is the second moment of area. Okay, and this has to be the least, so I is the second moment of area, and it basically the I is the least second moment of area. I should better point this out over here, and again let me show exactly what that means. So let's see if this is a ship or something, and what we do know that this ship, if it's floating in water, this will basically, the more inclination it will tilt this way and not this way, because you have two axes. One axis is passing through this, so it can tilt this way, or you have another axis, it can tilt this way. And what we do know from experience, that the ships tends to tilt in this with respect to this axis. So this axis will actually give you the least second moment of area, and we can I will do an example where you can see that this axis will actually have a higher second moment of area. So in this relationship, to find MB, we have to use the least second moment of area. Alright, so that's more to do with the definition, but exactly how we calculate some properties. So let me define that. So the procedure of evaluating the stability. So let's look at this. And these are the points that we have to do for all the examples we're going to do for the stability. So this is the procedure. So what it says is determine the position of the floating body using principles of buoyancy. So the first idea is we need to know exactly. So if I have to actually, yeah, let me draw it over here, and then I will be going along with as I. So the first thing we need to know, so if I write this first, how much this object is inside water. Okay, so from the principle of buoyancy, we can find out what is this distance or how much it is outside the liquid, but we need to exactly know how much is it inside the liquid, and that's determine the position of the floating body using principles of buoyancy. The second thing is locate B. Compute distance YB from some reference plane or axis. Usually bottom of the object is taken as a reference axis. So once we found out that okay, this is how much it is inside the liquid, so the center of that geometry or like that volume will be the point B where your force is acting, FB. So we will take some reference, and it can be anything. It can be this reference over here, it can be this reference, and we have to find this YB, and usually that reference is taken to be either the base of the ship, or you can take it as the whole plane or just an axis, because we have to reference it from somewhere. So I'm just going to take this point as the reference, and we will find out what that YB would be. So this gives me from this reference line to that buoyancy point B, so it gives me YB. And then I have to locate G, compute YG measured from the same reference. So in that case, I need to know what is the weight of this object and exactly where that weight is acting, and where that weight would be acting will be the point G. So that point is G, and somewhere over here, so I mean that distance is Y of G, and that is taken from the same reference line. So I have to make sure the same reference line is used to compute YB and YG. The next thing is compute the displaced volume. So we can find out what the displaced volume would be, because this gives us so you have the height of the fluid, then you will have the length and so on, the width of this, so everything. So we will be able to compute the volume, in this case length times width times the height. Okay, so this is point 4. After this, we're going to compute MB, which is equals to I over VD, where I is the least second moment of area for that shape. So in this case, if I'm looking at we have to find MB. So first of all, we have to find MB, and so somewhere over here it can be above or below. So we will compute that based on the least second moment of area. So based on if I look at from the top view, this thing, you will have one axis over here and you will have one axis over here. So if I'm calling this axis AA, this as BB, so what I do know from experience that IAA is the least moment of area. So IBB is greater than IAA, and in one example we will do that. Okay, so this is part 5, so point 5 to basically compute that. And after that, so once we have found out the distance of from point B, so distance from point B to M, so wherever that M is, it can be above or below G, so but we have found out this distance MB. Okay, so after that I can find out the distance of YM, which actually will be the YB from that reference line plus the MB, that's the line above. So that will give me the total distance of YM, which will actually be YB plus MB. And if YM is greater than yg, then this object is stable. As we discussed, that as long as the metacenter is above the center of gravity, it will be stable. If ym is below yg, it is unstable. Or the similar way I can say, if mg is equals to, which is ym minus yg, if mg is positive, it is stable. If mg is negative, it is unstable. So mg is, so once we have this distance m, so we can find out what this mg would be. And if mg is a positive number, this means that m is above g, then it's stable. If it's negative, then it's unstable. So those are the 6 things we always have to compute to find the stability of a floating object. So let me actually do a quick example and to show you exactly how this works. Alright, so here's an example, and I took this from Applied Fluid Mechanics by Mott. Okay, so the example says a flatboard hull weighs 150 kilonewton, location of G is given, find if the boat is stable in fresh water. Okay, so this is the top view of this boat. Again, it's a rectangular shape. I couldn't make the straight line here. So this is the top view, this is the front view. So we are given the distance of the center of gravity, so I can I can call this as yg. So I'm taking this line as a reference, and this distance is yg, and the total height of this is 1.4, and so on. So we want to find if this thing is stable or not. So the first thing we have to do, determine the position of floating body using principles of buoyancy. Okay, so we have to find out how much this thing is inside liquid. So basically, we don't really know how much this thing is inside the liquid, so that's the first thing we need to compute. Okay, so I'm gonna move this on the side. So the position of the floating body, so the way we can calculate this, so again, if you have this object somewhere over here, okay, so somewhere over here we have yg, which is 0.8 meters, and we want to find out exactly how much this is floating. So I can call this distance to basically be x. So x is how much this thing is floating inside the liquid, and we can have the vertical force is equals to 0. So the only vertical 2 forces acting on this is the buoyancy force, which is acting in this direction, and then the weight of this object. And the weight of this object is given to us, so I can make those equal. So the buoyancy force minus W is equals to 0. So what that gives me is the buoyancy force is equals to W. Okay, so the buoyancy force is equals to, so we have this quantity W, so but I also know that the buoyancy force is equals to gamma times the volume, where we have the gamma, and the volume of this object is basically length. Okay, so I'm gonna use the length times the breadth, because I don't want to use the width, because it will give me the same as this W. So length times the, so if I'm looking at it from the top, so so this is the length, this is the breadth, and then I have the depth of this, which actually in this case, as we want to find out how much this thing is floating, and that will be the displaced volume. So that in this case it will be x. Okay, so I'm representing this as x. So these are the multiplication signs, and this is the x. So I have this gamma because this is some water. So the gamma is so I can so I can write this as x is equals to W, which is the weight, divided by length times the breadth times the gamma of the fluid. Alright, so this is 150 kilonewton. That's the weight of the hull that's given to us. 2.4 meters times 6 meters times okay, so this is meter cube. This is 9.81 kilonewton per meter cube. So that's what this quantity is, and all of this put together, it gives me 1.06 meters. So this distance x is 1.06 1.6 meters, 1.06 meters. And the total height, as you would recall from that picture that we had earlier, so I showed you, so the total height of this object was 1.4 meters, and this thing is actually at a distance of floating at a distance of 1.06 meters, and that's what we computed over here. So that distance is actually 1.06 meters. Okay, so that was the first thing we had to compute. The next thing we had to do, as I can bring back, to determine the position of the floating body using principles of buoyancy, the next thing was to locate B and compute YB. So we have to find out where exactly this B is acting. So if I write this as 2, so locate B, which, I mean, if this is our body of 1.4, this is 1.06, so somewhere over here in the middle, because the position is somewhere, I mean, is a centroid, so that's where the buoyancy force is acting, so it should be half of this. So y of B is equals to 0.53 meters. And then the third thing is to find locate G, which actually in this problem is given to us, which is 0.8 meters. Okay, so that's the third thing, locate G, compute YG measured from the same reference. The fourth is compute the displaced volume. So the displaced volume is VD, which actually in this case is breadth times the length times the distance x, the floating object. So all of this put together, it gives me 15.26 cubic meter. Alright, so after this we're going to compute this MB, which is I over VD. So we already have computed this displaced volume, so let's look at the second moment of area, the least second moment of area. So in this case, if I'm looking at this object from the top view, and I have this axis as IAA and this axis as BB. So I can find this IAA to be equals to L, which actually in this case is this L, and this is the B. Oh, actually, yeah, that's okay. So yeah, I mean, so this is the width of this. All right, so this is the width of this thing. So L times width to the power third divided by 12. So I can find this comes out to be 6.91 meter to the power 4. If I want to find IBB, in that case it will be width time length to the power 3, and you will notice that length is much bigger because length is 6, this width is 2.4. so if I make the cube of this and then multiply it to the width, so IBB is greater than IAA. So we have to take the least second moment of area, so that's why I'm going to pick this quantity, and then I'm going to find my MB, which actually comes out to, I mean, which is I over VD, and then 6.91 meter to the 4 divided by 15.26 meters square, and that gives me 0.45. Okay, so this gives me 0.45 meters. So the last quantity is we have to compute Ym, which actually is Yb plus Mb. So after this I'm going to compute Ym, which is Yb plus Mb. So Yb was 0.53 plus 0.45, which actually gives me 0.98 meters. And 0.98 meters, and if you recall, the center of gravity was at some distance of 0.8, so our point Ym is 0.98 meters. So this thing actually will be stable. Okay, but as you will notice, there is no, okay, so for now I can say that so the degree of stability I can find this mg, which is ym minus yg, and in this case it is 0.98 minus 0.8, so it gives me 0.18 meters. And as we talked about, that even if mg is positive, so which is the distance from g to mg is positive, it will be stable. If it's negative, it's unstable. And the same way what we talked about, if ym is greater than yg, so that is fine. Okay, so the reason we want to find this mg, and this is mostly in the literature, and especially the people who have worked in this industry of building ships and stuff. So the small, okay, so why this mg is important? I mean, of course m has to be greater than that, greater than above g, but small seagoing vessels should have minimum value of mg of 0.46. Large ships should have mg, or sometimes it's also known as gm, but mg greater than 1.07 meters. At the same time, if the metacenter is 2, if metacenter height is too large, ship might MIGHT have an uncomfortable rocking motion. Okay, so uncomfortable rocking motion, and that will also give you, that causes seasickness. And that you can think about it like the higher this value of m would be, so when it tries to stabilize, it basically creates more rocking position. It will be more rock, it will create more rock, but at the same time the degree of stability will be even higher because you have a much higher metacenter. Alright, so the next thing is, again it's more of a discussion, so let's look at the stability curve. Okay, so in that case we only had a hull boat which was, okay, so it did not have any angle of tilt or anything, but let's define if we have some tilt also. So the stability curve, so let's look at that. So in this case, so let's suppose if you have the fluid somewhere over here, and then I'm gonna define this object, and so somewhere over here, and this is where your f of b is acting. Alright, so this is where your g is acting. Okay, so these two distances, and then I also have, this is where it intersect. So this angle, which I'm calling as theta, is called the angle of rotation. Okay, this point is b, this point is m, where these two intersect. This is m, this point is b, this is g. The distance, I can call this as bg, and this is also known as the rotating arm. Okay, and the idea is, so let me actually draw this curve. This is not the exact curve, but something similar to this you might see in literature. So rotating arm, which is bg, and again you can have it in meters, so 1 meter, 2, 3, 4 meter, 5 meters, and so on. And then on this axis we have the angle of rotation, which is the theta. So angle of rotation theta over here on these axes, so 10 degrees, 20 degrees, 30, 40, 50, 60, and so on. So the curve actually will look something like this. Okay, so you will have a steep, initially a lot less, and then it will be a steep drop. So as long as GH, so which is actually I'm calling this is my BG, or okay, so as long as this h, and I'm representing that as gh, but I should actually be calling this as g b. But so as long as this distance is positive, so as long as bg is positive, ship is stable. Okay, so in this case, as you rotate this even further, the angle actually will start increasing, and a point will come when this distance will start to drop, and eventually it will go to negative. So as when it goes to negative, then the ship becomes unstable. So to if you're designing a ship, so you have to keep this also in mind, that this will provide you the degree of stability. Alright, so that's pretty much what I wanted to say about this. Yeah, and of course, as this angle will increase, the m will actually